So, hi everyone, welcome to another LIC class. Before I start the class, do you have any questions from the previous class? Okay. So today I'm going to do a quick review of the previous class, which was different parameters and operations of an op amp. And after that, I would continue the parameters of an op amp, parameters such as the frequency response and slew rate and the response time of an op amp. So we learned from the previous class that op amp usually has 5 pins, 5 terminals. 2 of them are signal inputs. We have the inverting and the non-inverting input. 2 are the power supplies, DC supplies, which turn on and supply the power for the op amp. And one of them is the output. An op amp amplifies the difference between the inverting and the non-inverting input. The inputs of an op amp could be both AC or DC. So it could work as a DC amplifier or an AC amplifier. It could be used both in AC signals and analog and digital signals as well. The power supply, however, must be DC power supply. Normal packaging, the most popular one is dual inline, which I mentioned, and this is for a 741 op amp. The internal circuit comprised of at least 20 transistors. We have multiple stages of amplifiers using common emitter and difference amplifiers and so on. 3 main operations of an amplifier are the inverting amplifier, non-inverting amplifier, differential amplifier. We had the open loop voltage gain, which is infinite or very high in practice. Ideally, it should be infinite, which is the output voltage, the ratio of the output voltage to the input voltage. And then we had the closed loop gain, which is the controlled gain. When we give a feedback to the system, and usually that one is also pretty high, but much less than the closed loop gain. We had the input resistance, which is the ratio of the input voltage to the input current. Ideally, this should be infinite, but in reality, it's pretty large, around several mega ohms. We had the output resistance. This one should ideally be 0. In real world, it's a few, like 10 ohm, a few ohms, up to 100 ohms. We had the input offset voltage. An ideal op amp, the voltage difference between the inverting and non-inverting should be ideally 0 when we have no inputs. In the real world, there's a slight difference between them. We use the offset voltage to be able to counter that and cancel that offset between the input voltages. I already mentioned. And then 741, the offset voltage pins are pin number 1 and 5, and we connect them together with the potentiometer. We had the input bias current and offset current, the same thing. There's not a lot of things that we can do about the input bias current, but since it's pretty low, it's we can negligible. It's not very important. Then we have the supply current, which is the current passing through the power supply to the op amp, supplying the op amp. That's usually around 20 to 30 milliamps. We had the common mode rejection again. For an ideal op amp, the difference between the input should be 0. Therefore, when we connect them, the output should be 0. But in real world, because we have that offset input voltage, we have a common mode rejection, meaning when we connect them, we still have an output. And finally, we had the power supply rejection ratio, which this means that if the power supply voltage changes, the output shouldn't change while the input is fixed, but this doesn't happen. And usually when, sometimes when you change the power supply voltage, the output voltage changes with that as well. So the next parameter that we have is called the slew rate. So what is a slew rate? We have slew rate for in all type of different circuits, like transistors as well. Slew rate is the response time of a certain circuit. So what we do and how we determine a slew rate is we give it a step input or a square input, and we measure how long it takes for the output to match that input. So, and this is very important, especially in digital circuits. So what we do is for example, we give it a step input, and we would see that how fast it takes for that element or that circuit to follow that input and reach the desired value. So for example, if we have a capacitor and we want to charge a capacitor, imagine that we have a capacitor and we want to connect that capacitor with a switch to a battery. Okay. When we close that switch, it's like we are giving it a step voltage. Ideally, the capacitor should charge immediately and follow that step. But in real world, it takes time for that capacitor to charge, and that's called the response time, okay? The larger the capacitor is, it's gonna take more time. So you're gonna have different slew rates based on different capacitors. If you have a large capacitor, it's gonna take longer. If you have a small capacitor, it's gonna take less time, okay? So slew rate, this rate and the speed, which is the ratio of the V output to delta T. This is called the slew rate, or this slope, I could say, determines how fast the system could respond to an input signal. So the slew rate is measured by this equation. It's the delta V out over delta T, delta V difference to delta T, to this difference. Where delta V out is the change in input voltage, and delta T is the corresponding interval of time. Slew rate is measured in volts per second or volts per microsecond, and typical values range from 0.2 volts per microsecond to over 20 volts per microsecond. So slew rate imposes a limitation on circuit in which large amplitude pulses rather than small amplitude sinusoid signals are likely to be encountered. So imagine that we have a switching system. Let me add another slide. So instead of that capacitor, imagine that we have a very large capacitor or something like that. But this time, instead of just having one step signal, we have a square signal that goes like this, okay? And my input signal is something like this, okay, a sinusoid. If my slew rate or response is very fast, I'm going to have a clean signal at the output, meaning I can have something, and let's do this to become positive, negative. Let me extend this. Imagine this is a positive, negative, something like this. So if this pulse is wide enough, I'm going to have a perfect response, like something like this, okay? What happens if the timing is too short, meaning instead of having that pulse, I have a very small pulse. Now, the signal cannot follow that pulse. So it's going to be cut off at this point. Suddenly, you're going to come back. And then suddenly, you're going to go back. So instead of having a sinusoid, you're going to have something which looks like this. So you're going to have a distorted signal. Okay? Let me put it this way. Imagine I give you a problem. Like I give you a multiplication problem. Or I tell you to add 3 plus 2 plus 1 plus 4. Okay? And imagine that finding the solution to this problem takes you 5 seconds. So now, if I give you 6 seconds to solve this problem, everyone is able to solve the problem. But what if I give you 3 seconds? You're only able to solve, for example, or 2 seconds. You're only able to add 3 plus 2. So you're going to have half the answer. You're not going to have the full answer. That's exactly what happens to signal. You're not giving enough time to the signal to fully be able to respond to that output. So you're not going to have a full signal. You're going to have a distorted signal. You're not going to have the full solution. You're going to have a partial solution to the system. Okay. So instead of having a clean sinusoid in the output, you're going to have a triangle signal, for example, a distorted signal in the output. Is it clear? Or let me give you another example. For example, imagine that I'm going to send an image on internet from point A to B. It takes 10 seconds for that image to be sent, or that video. And what if the connection is cut in 5 seconds? You're going to get half of that image. You're not going to download the whole image. So you're going to have a distorted image. There are other ways to channel that, like reduce the quality and so on, but that's I can say slew rate response in a nutshell. So you need enough time, or you need a faster system. So instead of having 6 seconds, if you use a calculator, you can do that in 2 seconds. Yes, if I give everyone a calculator, you can calculate that in 2 seconds. Now, 2 seconds would be enough to solve this. So there are 2 ways. One, I can give you more time. More time means a wider clock, or more time, lower frequency, because higher frequency means a faster. High frequency looks like this, and lower frequency looks like this. So you need a lower frequency, or you need a faster device. So instead of using your brain, you can use a calculator, for example. Or for the internet example, instead of using cable, you can use a fiber optic, which is faster too. Most of the time, we don't have any, we don't want to change the frequency. We want to have the system as fast as possible. Therefore, we should use a faster op amp, I could say. Now, if this op amp had a perfect and instant response, if the input looks like the black one over here, this one, the output should look pretty close to it, okay? If I had like an almost perfect response. But we don't have a perfect op amp. Therefore, when the input changes, the output takes some time to follow the input. And you can see that the signal is slightly distorted. Instead of having a square signal, you have this type of triangle signal. So if I have a better op amp, it's going to look more like a square. If I have a worse op amp, it's going to actually look like a triangle. Okay. Now, and how do we measure the slew rate? It's going to be delta V, which is this, over the delta T. Okay. So how fast can I go from point A to B in a shorter time? And why is delta V important here? I always give this example, and it's the same for digital systems as well. Imagine I'm on the floor and I want to jump on this chair or on this table. Which one can I do faster? Jumping on the chair or jumping on the table? The chair. So if I have a smaller delta V, meaning this is a smaller value, I can easily jump between them, okay? So if I have a smaller delta V, it's going to be easier. But if I have a pretty high, like if I want to jump from here on this table here, it's going to be take longer for me and more energy would be consumed. So lower delta V is actually better, okay? And the other thing is higher delta T. So if I have more time, it's the exact same example that I gave you with the math problem. I have more time, I had 6 seconds, I can solve it. But if they give me 2 seconds, I can't solve it. So that's the important part. Okay. But if a system is capable of doing 20 volts per microsecond, it means this is a more powerful system. It could do more than the system that could do 0.2 volts per microsecond. So this means that this is a much powerful and faster system because it's capable of jumping from here up here, which is 20 volts in 1 microsecond, compared to another system which could jump from the floor to the chair in 1 microsecond. So the system that could do more in the same period of time is a faster system. Does it make sense? Yes. So if I could jump higher in 1 microsecond, it means I'm a faster, a stronger person, or a stronger op amp in this case, faster op amp, compared to the op amp could just jump from the floor to the chair. Okay. So a 20 volt per microsecond system would look something like this, which is much closer to the ideal. So this is 20 volts, for example, and this could be like a 0.2 volt. When the op amp becomes faster, it becomes much more expensive. And usually we don't have those very fast op amps in high power situations. We usually have them in electronics, not electrical systems. We have limitations on power as well. Okay, so now that we learned about slew rate and the response time, which is technically the slow, the next parameter that we have is called the full power bandwidth. So before I start that, how many of you are familiar with frequency response and bandwidth? Okay. So frequency response means if I have a circuit, doesn't matter what circuit I have, and I give it a very small frequency, low frequency, and I increase that frequency gradually. So imagine I'm starting for DC, which has a frequency of 0, and I slowly increase the frequency. I want to see that how fast this system can respond to this frequency. Imagine that this is, for example, an op amp or a transistor or anything. You can compare this again to what I mentioned about jumping on the chair. I want to see in 1 second how many times I want to jump in this chair. I have a limitation. Okay, so for example, imagine in a minute, the maximum times that I can jump on this chair is going to be 20 times. So my upper limit is 25. Okay, some systems have a lower limit. It's like a speed limit on a highway. You can't go, for example, over 75, but in a highway you can't go under 45 as well. Okay, so you have a speed limit. Those speed limits are called the frequency response in the system as well. And we show that with a frequency response graph, which looks like this. And in this frequency response, and this, by the way, this is the frequency, and this is the amplitude. It's exactly like a speed limit that you have on a highway. For example, if you have 75 miles per hour and 45 miles per hour, this is what we call a frequency response, meaning that our system works in this frequency or in this speed, but over that speed limit, our car is not capable of going, or we have restriction, and under that, we have the same restrictions. So you may ask how we determine the speed limits or the cutoff frequencies of the system. So the cutoff frequencies or the limitations in this system are determined by the gain, the voltage gain. And we determine that by using this equation. The cutoff frequency would be square root of 2 over 2 of the maximum gain, or in other words, 0.707. Square root of 2 is 1.41 over 2 is going to 0.707 of maximum gain. So if the gain here is 1 or AV, when the gain reaches 0.707, or we have a 3 dB loss, I'm not going to go into detail. This is like a whole course. That is our frequency response. Okay. What does this mean? Imagine again the car scenario. If you go over that speed limit, so your car has a speed limit. Imagine your speed limit is 100 miles. If you drive more than that, what's going to happen? You're going to damage, for example, the engine or the gearbox. Okay, it's the same here, and when you damage that gearbox or transmission or motor, the speed is going to fall again. So after these speed limits, the frequency response and the gain is going to drop. So that's what actually happening. You have a limit, upper limit, and the lower limit. This is called the FL, or the lower frequency, and FH, or the higher frequency. And this is the frequency response, or we call it the bandwidth. The bandwidth is the frequency which the system works in. So for example, this bandwidth could be between 10 hertz and 1 megahertz for an op amp. Meaning, if you give a frequency which is higher than 1 megahertz to an op amp, the op amp output would significantly drop, and you're not going to have any output from the op amp. So you may ask what happens, for example, in a lower cutoff frequency. If you have a capacitor which is connected to an op amp, and this is connected to the ground, and this is connected to the input. If I give it a frequency, imagine for like example 50 hertz, that frequency is going to easily pass the capacitor and reach, so you're going to have no problem. But what happens if I give a DC signal to this. When I give it a DC signal, the impedance of the capacitor, 1 over J omega C, if you remember, that's going to significantly increase. And the capacitor, when you have a DC signal, is going to act like an open circuit. Therefore, you're going to have no signal going inside, or I in would be 0. Therefore, you're going to have no signal in the output as well. And this capacitor is called what we call the coupling or bypass capacitor. These are usually large capacitors. These capacitors determine the lower cutoff frequency. Okay. If I didn't have that capacitor, the cutoff frequency could go down to even 0 hertz. So I would have no lower cutoff frequency because even a DC signal would pass through and I would have an output signal. Okay. And then I would create what is called a low pass filter, or LPF. Okay. A low pass filter is the filter that passes all the low frequencies and it cuts after a certain frequency. So very high frequencies will not pass. I'm going to explain more about low pass, high pass filter, and notch filters. This is the principles in a nutshell. I'm not going to get ahead of myself. And the high pass filter and the higher cutoff frequency is determined by the inner capacitors, like these small capacitors that exist between the pins of a transistor. As I mentioned before, in very high frequencies, the terminals of these capacitors, because they are metal, they create a capacitance. And with very high frequencies, these become short circuit and they completely short circuit the op amp, and the op amp becomes useless. So lower cutoff frequency, you can change it. We have power of it. Higher cutoff frequency, because it's the internal structure, and you can't change the internal structure of op amp. Usually, we don't have control over it. You have to change the op amp entirely. So now that we learned a little bit about bandwidth, so this is a brief explanation again about what I mentioned. The full power bandwidth for an operational amplifier is equivalent to the frequency at which the maximum undistorted peak output voltage swing falls to 0.707 of its low frequency. Typically, full power bandwidths range from 10 hertz to over 1 megahertz in op amps. Some transistors could go over gigahertz. We have very high frequency transistors as well. The full power bandwidth, or FPBW, of an op amp is the maximum frequency at which slew limiting doesn't occur for rated voltage output. It is important to realize that both slew rate and full power bandwidth can also depend somewhat on the power supply voltage being used and the load the amplifier is driving. The reason that the power supply affects this power bandwidth, as I mentioned again, if you have a higher power supply, like what I had, the example that I had, jumping between the floor and the chair or the floor and the table, when you have a higher power, you need more time. So therefore, you need a faster system. So it limits your frequency response as well. So slew rate determines the speed of the response. And that speed of response determines the frequency, the bandwidth in which your system can operate. Okay. So this is an example of full power bandwidth. And if it's not enough, the output would be distorted, exactly like what I showed you in this picture, which creates a triangle signal. So, yes, please. Yes.
So if you're sending a discrete signal input,
yes.
As we looked in those previous slides.
Yes.
As long as your output reaches the max voltage of the input.
Yes.
You're still going to have a good signal coming out.
Yes, that's a perfect expansion, yeah, and it's a great question. And one thing that I wanted to add to that is that in a digital system, you never have a square signal, okay? What you're gonna have is it's something like this that looks like, you know, as long as this reaches that threshold in a digital system, it's acceptable. This is accepted as 1, 0, 1, 0, something like that. So sometimes it's distorted, but you still get the information out of it. And that's a great point. Yes, it doesn't need to be a clean square signal. It could be something that looks like this. But as long as it reaches not even the maximum input or output, like voltage, even like 80%, sometimes 80% of that is enough, okay? And that's what we call, we have a threshold, and we have you would see that in digital design if you have digital design. We have a threshold between these, and we have a band between them. So anything upper than that threshold would be accepted as a 1 or a signal. Okay, so yes, that's completely correct. We would always have slew rate and distortion, but if we retain like 80-90% of the signal, it's still acceptable. And that is determined by something that we call the SNR, signal to noise ratio, and that should be above a certain point. And that depends on the application. Let me give you an example. So our ears are, as I mentioned, capable of hearing up to 20 kilohertz. So anything above that, we can't even hear it, okay? So if I have a signal that is 30 kilohertz and I lose like 10%, you can't even hear it. So that's not going to be a big deal. But if you are working with medical signals like an electrocardiogram, which is a heart signal, that could create some problems. If you have a lot of distortion, then the signal would have distortion, and the doctor would think that the person has a heart problem. Okay, and I worked with a lot of EKG, we call it ECG or EKG, electrocardiogram, and PPG with the polysmogram signals. So in medical devices, you need very high quality signal outputs. Therefore, we usually use very expensive op amps. That's the reason the MRI device costs $1 million, and a oscilloscope costs 50, because it depends. High frequency needs very that's MRI obviously is very complicated. You need like these superconductors, and like you have to inject helium, and it's very complicated device. But an EKG device, for example, and which is technically a type of oscilloscope, that is like $1,000, and you can buy an oscilloscope for $50. So that's the reason you have to have very high speed, I could say, op amps and that, which are very expensive. Even the process of building them, you have to have protected shields to reduce environmental noise and so on. So it makes it very expensive. I hope this answered your question. Yes, okay. So distortion is acceptable to some point. It's a limitation of the system. We can fix it to a certain point, but after that, we don't have any control of it. So, sorry. So let's go back to the desirable characteristics for an ideal op amp. What are we looking for, and what's desirable for an ideal op amp? So first thing is that the open voltage gain should be very high. Ideally, it should be infinite. The input resistance should be very high. Again, ideally infinite. The output resistance should be very low, should be ideally 0. The full power bandwidth should be as wide as possible. Slew rate should be as large as possible, meaning it should be higher voltage to the microsecond. I mentioned 20 volts compared to 0.2 volts per microsecond. Input offset should be as small as possible. Two things that you should remember, that these are the two most important things that you need to know in an op amp, is that always for an ideal op amp, V positive is equal to V negative, which are the input inverting and non-inverting, and the input current is 0. Just knowing these two, you can solve like 50% of op-amp problems with a simple KVL cell, and I'll solve more practice problems. So for an ideal op-amp, these are the most important things. The negative input voltage and the positive input voltage are equal. The input current to the op-amp is 0. So, for example, if I have a op-amp which has a voltage source connected to it as 2 volts, what is the voltage here? I'm gonna call it Vn. Since V positive is, which is this voltage, is always equal to V negative, which is equal to 2 volts. So V positive would be 2 volts. And what is the current going inside? 0. Okay. So always they would share the same voltage, and then they are even connected to one point. And the input current is always equal to 0. Now, what is the difference between an ideal op-amp and a real world op-amp? So for an ideal op-amp, the voltage gain should be infinite. In real world, it's like 100,000. The input resistance is infinite. In real world, it's like 100 mega ohms, which is still pretty high. 100,000 is also very, very high for the voltage gain. The output resistance is 0 for an ideal op-amp. For a real world op-amp, it's 20 ohms. Bandwidth is infinite. For a real op-amp, it's 2 megahertz. Slew rate is infinite. For a real world op-amp is 10 volts per microsecond, and the input offset voltage is 0 for an ideal op-amp, and for real world op-amp, it's less than 5 millivolts. So let's solve a practice problem. So we have the following op-amp, for example. V out is equal to 15 volts. Vn is equal to 250 millivolts. Let's see. I'm going to give you an example that you can solve. The input current is 5 milliamps. Let's make this 5 microamps. And it takes 5 microseconds for the output voltage to go from negative, or let's do this, go from 0 to 15 volts. We want to find the gain. We want to find the input resistance or the input impedance, and we want to find the slew rate. I'll give you a few minutes to solve this, and I'll
-6, right?
I'm sorry?
Micro is 10 to the -6.
Yes, micro is 10 to the power -6. Milli at 10 to the power -3, micro 10 to the power -6. Okay, did anyone solve this? Give you a few more minutes. Our class is until 10:20, yes?
We solve for AV.
Yes, first for AV, which is V out or VN, 15 volts over 250 millivolts. What was the answer for this? 60, perfect, 60. Rn is Vn over In, which is 250 millivolts over 5 microamps. So this would be what? 50K, yes, 50,000, perfect. So 10 to the power -6 goes up, so it's going to be 250,000 over 5. It's going to be 50,000 or 50K. And so slew rate is going to be delta V over delta T. So voltage is, yes, perfect. It's going 0 to 15, so delta V would be 15 volts divided by 5 microseconds. Thank you. It's going to be 3 volts over 1 microsecond. Okay. So, did you write this down? So this is going to be your first homework. I'm going to post it on Blackboard as well. You're going to have 1, 2, 3, 4, 5. I'm sorry, 4 questions. You're going to have 4 questions. I wanted to, with the solutions, everything. And next week I would post the solutions as well. Pretty easy, same thing that we did right now. It's going to be your first homework for next week. And you're going to have until next Thursday to solve it internally. I will put a Dropbox on Blackboard. The homework, you click on it, you can easily upload it. Please just upload your homeworks in a PDF format and make it clear when you take a picture. That can easily. Do you have any questions?
Can we use notebook paper?
No, in the regular, any paper would be okay. Even if you do it on your iPad or anything, take a screenshot, send it. That's even better. Okay. As long as it's clear, I don't care what paper it is. Okay. Okay. Do you have any questions for me? No. So thank you so much. I will see you next Tuesday.